Hello friends, welcome to our channel. Let's have a look at a newest problem, that is problem 3686, number of stable subsequences. This problem is a counting problem, and we are going to solve it using dynamic programming in this video. First, let's quickly look at the problem statement, and then we try to digest the logic. So we want to count the number of subsequences that are stable, right? In other words, count stable subsequences. So in the sense of modulo this big prime number, 10 to the power 9 plus 7. So first thing we need to notice is what's the definition of stability or stable subsequence here. It means that it does not contain 3 consecutive elements with the same parity. So in other words, for this problem, so though we are given a nums list, essentially we just need to consider 0 or 1 in the sense of modulo 2 of these numbers, right? But that's not essential, but this is the one point we need to notice. So with that said, you can look at the 2 examples. So in the first example, the output is 6. The one which is not a stable subsequence or sequence is 135, because all the 3 numbers are odd numbers. In example 2, the output is 14. The sequence that is not stable is 2, 4, 2, because they're in modulo 2, they're all zeros, right? So first point. So essentially you are working with this one. So y modulo 2 for y in nums, right? So in other words, it's 0, 1s or parities. The specific numbers do not count for the number of stable subsequences. So that's the one thing. So here, actually, what we want to do is using dynamic programming. And for this problem, I'm going to use this notations. So odd is the number of stable sequences ending at the current index we are looking at. So number of sequences ending at the current index with the last element with a single odd element as the tail. So that's the one. And also say less as a tail, and odd and odd, so basically the same thing, but the number of stable subsequences at the ending are so far, and with 2 odd elements as a tail, because for this one, for the first one, you can append odd elements, even elements, right? For this one, you can only append even elements in order to form stable subsequences. Similarly for even, so it's the number of so let me just copy this part with a single even element. So here, let me copy this one, and the even. So the number of stable subsequences ending at the current index with 2 even elements as the tail, right? So for example, for even and even, you can only append odd elements to form new stable subsequences. So once you realize this, so this is the notations and the interpretation. So as all we know, for using dynamic programming, especially in terms of tabulation, so the interpretation is very important, right? So once we do this, so our focus will be on DP update, right? How do we update those numbers? And the final return should be the summation of this odd plus odd plus even and plus even, and then modulo the big constant m. So we can use m to be 10 to the power 9 plus 7. So notice that you can check 10 to the power 9 plus 7 is a big prime number, right? So in our coding, so we will focusing on the DP update. So actually you will observe a pattern. So thus you realize that actually the problem, though marked as hard, it's in some sense straightforward. So now let me copy this part. And then I'm going to initialize those numbers odd, 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 even, even, even to be 0. Because this odd, those numbers are immutable, so we can initialize like this. Or if you like, so you can do this, right? This is also good. Because if you do this way, the code is longer, but in my opinion, it's more clear. You can add some annotations like those here, right? Something like this. So this is some preparation, right? So finally, we just need to return this one. So then our focus will be how to do the DP update when we process this numbers. So basically for y in nums, so here I'm using y, not x, because sometimes x is interpreted as multiplication. So in order to avoid that potential ambiguity, I'm using y, right? So then we want to check if the current y is odd or even. So first, if y, here I'm using bitwise operations. So if this one has a result in 1, it means y is odd. Or you can use, say, if y modulo 2 is 1. That's also good, right? So if this is the case, first we can do this. Because y is odd, right? So y is odd, I can add y to each sequence ending with a single odd number as tail, right? So this way you will get odd, right, as tail. So in other words, the count of odd element will be incremented by that of the number of odd sequences, right? This is the one. Another thing is that we can count single element sequence. So this single element sequence by definition is always stable. So in other words, we're counting this y. So this way we add odd, increment odd by 1. So notice the order here is very important, right? We cannot first increment the odd, then do this line. So this line must be above this line. So this is another one. And then we can add this y to each sequence ending with a single even number. As tail. So now we get even odd, right? So this case corresponds to so the number of odd is, because you have one single odd, right? So it's going to be incremented by the original counts for even. And also you can add, so let me copy this one. You can add y to sequence, each sequence ending with 2 even numbers to form this plus even and even. Still, it's contributing to a new sequence ending at a single odd. So odd is incremented by even, even. Odd is even and even. So these two lines, the order does not matter. So you can write this one first or this one first. But here, this two, the order is important. So once we've done this, so because in the final return, we want to return the count modulus m, we can do this here. We can add the two line, modulo equals m, and odd, modulo equals this m. So this is the one block, right? Otherwise, so y is even. So if y is even, so what we can do, first we can add y to each sequence with a single even number as tail. So we form this even, right? So this will even is incremented by the original count of the even ending at with a single even number. So this one, and then we can count single element subsequence. That is this y itself. So we increment the even by 1. So now we can add. So here you can understand this add as append. Add y to each sequence. Ending with a single odd element as tail. So this you will get odd and even, right? So then still the contribution to even will be incremented by the original odd number of odd sequences with a single odd as a tail. So now you can add y to each subsequence, ending with 2 odd elements as tail. So you will get odd, and even. This even is this y, right? So then what you get is the new subsequence is ending with a single even element. It's even plus odd, right? So again, in the similar pattern, so we can do even modulo this m, and the even modulo this m, right? So once we finish this for loop, so we can return the count. So we have already read that. So this will be the full coding structure. So notice that. So we initialize these 4 numbers with the above interpretation. Then we do a linear scan, and then finally we return the result. Before we make any comments, let's first run it. Yeah, it passes the 2 test cases. So now let's look at the generic case. Yeah, it passes the generics in a very fast fashion. So then if we examine the code, so actually we can always print out this this number. So you can do something like this for I, y in enumerate nums, and then you print current count. So the current total count, right? So also we have this step I, the current count, right? So now let's run it. So if we look at the first one, if you are here, right? So you have 1 stable sequence. If you are at the index 1, so you have 2 numbers. 1 is 1, 3 is 1, and 1, 3 is 1. So you get 3. And if you are ending at 5, the increment is 5. So ending at 5, you can have 5 itself. You can have 3. You can have 3, 5, right? You can also have 1, 5, right? That's the 3 more. In total, you get 6. So now if we look at example 2, so when you at this first index, you get 1. And the second index, again, you get 3. And this index, you get 7, one more than this one. The reason is that in the first example, it's 1, 3, 5. They're all odd numbers. But here, we have 2 even numbers, 1 odd number. You can count 2, 3, 4. That's why you have one more than the first example. So then any and 2, you will get 7 more. So the 7 more is like this. You have 2 itself. You have 2, 4. You have 2, 3. You have 2, 2. And you can have 2, 4, 3, right? You can have 2, 3, 2, right? Those are the 14, right? So with that said, I guess that's it for the current video. Thank you for watching.